Welcome everybody to Microfluidics 1. Today's lecture is titled Fluid Properties. So at the end of this lecture, you should be able to name the properties that lead to different flow behavior of different liquids, as can be seen in the first picture. Or you can name the properties that become relevant when you're considering, for example, free surfaces or any kind of two-phase flow, as can be seen in the second image. So at the end of the lecture, you should be able to name the different states of matter and explain how they differ. You can name and classify state variables. You can name the fluid properties and describe how they depend on those state variables. And you can explain the difference between the microscopic and the macroscopic approach, a quite handy tool we are going to use quite often in this whole lecture to explain different phenomena. Today's lecture is structured as follows. You're going to see 3 videos where we are going to discuss the different fundamental aspects. And then we will meet in person and discuss those videos and go into some detailed discussion on the ideal gas law and how the continuum assumption in microfluidics works and if it is justified. Okay, so let's start with the 4 states of matter. Most of you should know that there exist 4 states of matter, namely solid, liquid, gas, and plasma. So each substance can be in those 4 different states of matter. And what we're going to look at now are the phase transitions between those states. So if a substance is becoming liquid, so it is a solid, and then it changes into the liquid state, we call this process melting. And when it's the other way around, the process is called freezing. When a substance changes its state of matter from liquid to gas, we call it vaporization. And the other way around, one speaks of condensation. For the change between gas and plasma, this process is called ionization. And again, the other way around, it's deionization. And now we are missing just 2 more changes. The change from solid to gas, which is called sublimation, and vice versa, the change from gas to solid, which is called deposition. And now we are going to talk a lot about fluids. So we have to ask ourselves, what is a fluid? And a fluid is a substance that deforms under an applied shear stress. And this means that this substance is able to flow. And when we are looking at those 4 states of matter, we can immediately see that under an applied shear stress, liquids and gases will move. So we consider liquids and gases as fluids. And when you think about these 4 states of matter, you have to make yourself aware that the state of matter depends on the environmental conditions. Meaning if a substance, if it is a solid or if it is a liquid, depends on the temperature, pressure, and so on. Let's have a more detailed look at the 4 states of matter, starting with solids. In a solid, the molecules are bound by strong forces, and there's no movement possible, but vibration is possible. So each of those atoms which make up a solid body is allowed to vibrate a little bit among its position. And if we now increase the energy of this solid, the substance becomes a liquid. And in a liquid, the molecules are still bound strongly enough to create adhesion, but they are too weak to prevent movement. So the individual molecules of this liquid, as you can see here, they still stick together, but they are able to move around. Liquids are considered to be nearly incompressible. And as imaged on the right, they assume the shape of the container they occupy. And if we now increase the energy even further, the liquid becomes a gas. And you can immediately see that the gas is quite different from the liquid. The molecules are separated so they can move freely. And because there's so much space between those individual molecules, gases are compressible fluids. And one remarkable difference between gases and liquids is that the gas fills the complete space of the container it is stored in. And if you now increase the energy even more, you get a plasma, and a plasma is partly or completely ionized gas. And in a plasma, the electrons and ions can move freely in space. Okay, we already discussed that the state of matter depends on environmental conditions. And if you want to know which state of matter your substance is in, a phase diagram is quite handy. Phase diagram is a diagram where you have the pressure on the y-axis and the temperature on the x-axis. And as you can see immediately, a phase diagram consists of different areas, and each area represents one state of matter. For example, in this area, our substance is a solid. If we now increase the temperature, our substance becomes a liquid. And if we now decrease pressure, our substance becomes a gas. And as we already discussed, there are the phase transitions, which you can see now on the right-hand side. So every time a substance changes its state of matter, you can just think how the process is called. And now we only have to discuss those lines which are into those diagrams, the so-called phase boundaries. And on those lines, you have two states of matter at the same time. So if you have, for example, this pressure and the corresponding temperature that you end up on this line, your substance is solid as well as liquid. So part of the substance will be solid and part of the substance will be a liquid. And of course, where the three lines intersect, you have a triple point. So at exactly this point, your substance is present as a solid, a liquid, and a gas. And the other point that is quite important is the critical point, which is somewhere here. And beyond that critical point, meaning at higher temperature or higher pressure, a fluid becomes supercritical, and then it's neither liquid nor gaseous, it's kind of undefined. So material or fluid properties are therefore always referring to a specific thermodynamic state given by usually the pressure, temperature, and volume. And when we are talking about a thermodynamic state, we have to discuss some wording. So let's start with the state variables or state properties. These properties describe the state of a system. So a common example is the pressure and the volume and the temperature, which define the state of that system. And those state variables are typically related by a state equation. For gases, for example, this is usually the ideal gas law, which we're going to discuss later in more detail. And in contrast to that state properties, which define your system, you also have material or fluid properties. So usually those are called material properties, but we also call them fluid properties because we are dealing with fluids. And these properties describe the property of a material, just as the name suggests. An example would be the viscosity of a liquid or the density. And you can now also classify those two property groups. You can classify each property as an extensive property or an intensive property. In extensive properties, they are proportional to the amount of matter present. So an example would be the mass. And in contrast to that, intensive properties are independent of the amount of matter present. An example would be the density or viscosity. Just imagine you have 1 liter of water. If you add another liter of water, your density of the water isn't going to change. Neither is your viscosity. So intensive properties are independent of the amount of matter present. So now I would like to discuss some variables in more detail, and I would like to start with the pressure. The pressure is an intensive property, and it's defined as force per unit area, and it's usually given in SI units as Pascal. So if you're working with pressure, please double check which unit you're using, because pressure is often given in non-SI units, such as pound per square inch or bar or atmosphere. So always make sure when you're working with pressures that the units match. And you can imagine pressure when you look, or if you consider individual atoms or molecules in a box. And this is illustrated right here on the right-hand side. So the orange dots are individual molecules, and each of these molecules has a certain velocity. And from time to time, one of those molecules is going to hit the container wall, as indicated here or here. And when it hits the wall, a force will act on that wall, and the atom or molecule will be deflected. And the force that acts on the wall can be interpreted as a pressure. Okay, so the higher the pressure, the more hits there are from atoms inside the container on the container wall. And this is how we imagine pressure if consider individual atoms. And on the right-hand side in the lower part, you can see some common values of pressure. So the pressure at sea level. So for example, when you're working in a lab, you can consider the environmental pressure to be 1 atmosphere. And of course, atmospheric pressure depends on the height you are at. So if you are on the Mount Everest, you have 0.33 atmospheres. The next property would be volume. Volume is an extensive property defined as space, for example, occupied by a fluid or gas. And we already discussed this difference between liquids and gases. And one of the main differences is that the liquid volume does not change with the size of the container. So if you would double the width of this container, the volume of the liquid would be the same. It would be less high, of course, the filling height would decrease, but the volume of the liquid would be the same. In contrast to that, if you increase the volume of this container, which is filled with a gas, the gas volume would also double, because the gas volume always corresponds to the size of the container it is stored in. And now let's discuss temperature. Temperature is an intensive property, and it relates to the vibrational energy in a solid or the kinetic energy in a fluid. In the solid case, you can imagine temperature as follows. The faster the individual particles vibrate, the higher the temperature of the material is. And you can define temperature by the expansion value of the kinetic energy. So if you look at this equation, on the right-hand side, you have, if you consider a gas, a mean velocity. Again, if you consider multiple atoms or molecules, they all have different speeds, different velocity vectors. But you can define the mean velocity of this gas volume. And if you then calculate the kinetic energy, which is done here, you can relate that to this term, which includes the temperature and the Boltzmann constant. And using this equation, you can define the temperature of a fluid in terms of kinetic energy. The next state property is the number of molecules. This is an extensive property, and it is closely related to volume and pressure. You can always think of it like this. The more molecules you have, the larger the volume is, or the higher the pressure is if you have a constant volume. So the number of molecules is closely connected to the other two state properties we already discussed. And the last state property we are going to discuss is the entropy, which is quite useful. I think most of you should have heard of this state property. It's often used in thermodynamics, and it's very useful to explain reversible and irreversible processes in thermodynamics. And it is related to the degree of disorder of a system, or more precisely to the total number of possible physical states of the system. So what does this mean? For this, you can look at the right-hand side, where we have two volumes, two gases, the green gas and the blue gas. They are in a container, and they are separated by a membrane. And if you now remove this membrane, of course, you know that those gases will start to mix. And why do they do this? Why do those two gases mix? There's no force that is driving them to mix. You do not steer the gases. And the reason for this can be explained using the entropy, because if you look at state 1, the system is highly ordered. The gases are separated, so it's quite tidied up. And if you look at state 2, it looks more chaotic, so it has more disorder. And so the state 2 has more entropy than state 1. And usually in thermodynamics, you can always say that a system tends to maximize its entropy, so it will become more chaotic. And this is why the entropy is so common in thermodynamics, because you can explain processes which are otherwise hard to explain.